Okay, let's talk about the section 5, Weierstrass factorization theorem. Okay, so we already studied the zeros of functions, analytic functions. Analytic functions, if it's not a constant zero function, then the zeros of analytic functions will not have a convergent point, the limit point inside the open domain. So that's a property. When we have a function, we can study its zeros. Now the converse problem will be the following. So given a sequence AK in G, which has no limit point, no limit point in G, okay, and a sequence of integers. Integer, here integer we mean the non-negative integers, mk. Okay, so those are the given conditions. Is there an analytic function f on G such that the only zero of f are at AK with multiplicity of the zero AK equal to mk. So we want to design some analytic function with a specific zeros AK and with a specific multiplicity mk. Okay, so this is the converse problem. It's a converse problem. So previously we have a function. We study its corresponding zeros. Now we have a bunch of points. We want to say, is there a function with those points as zeros? Right? Well, why we study this problem after the compactness and the convergence? The thing is that if there are only finitely many points, for example a1 up to am, then this problem is trivial. Then function f of z, the polynomial function z minus a1 to the power m1 times z minus I use m, let's put k here, I need m, z minus ak m to the power mk, then this polynomial satisfies the condition. Right? So if we only have finitely many elements, then this problem is not interesting because it's trivial, already solved. So if you have infinitely many point AK with MK, then you are going to have infinite product. If there are infinitely many points AKK from 1 to infinity, then f of z would be some type of infinite product. Well, infinite product, some type, we're going to study what type, what condition we need to make it happen. So whenever you have infinite stuff, it is related to the convergence. It is related to the convergence, right? So that's the reason we study this Weierstrass factorization theorem after the convergence. We have to solid get the convergence. And we know that the HFGs is complete, closed. So we're going to construct some finite product and take the limit, and we get the convergence. And that limit will be also analytic, because h of g is analytic, right? Okay, so now we're going to see the infinite product. We already, I mean, even in the calculus, we learn the infinite sum, the series. So we have the infinite sum. And infinite product. They are very closely related, but they are slightly different. Remember, for the infinite sum, there's only one type series. One type of series, which is trivial. It's like a 0 plus 0 plus 0 plus 0. You just get infinitely many 0. You add them together, it's still 0. That's a trivial case. This is the only trivial case. But for the infinite product, if one of AK, let's put the ZK, we're talking about the complex number. If one of ZK is 0, then assume we are talking about infinite product. This is infinite product. This product will be 0. So you have a lot of a trivial case, right? So you have a lot of the trivial case. Whenever one of the element is 0, then the product will be 0. So let's make the infinite product is slightly make it slightly different from the infinite sum. Infinite sum, this is the only trivial case, but infinite product, you do not study the case if one of the element is 0. Okay, so we're talking about the product of infinitely many non-zero element. Infinitely many non-zero element. So we only study the infinite product of infinitely many of a non-zero element. Non-zero elements. Okay? Only non-zero elements. All right. Well, let's see the definition. What is infinite product? If Zn is a sequence of complex numbers, and if Z, which is a limit n approaching infinity, okay, and then remember, in the infinite sum, we have a partial sum. In the infinite product, we have a partial product. We first get the product of first n element, and then you will have a partial product, and then you take the limit. If this limit exists, then the limit Z is the infinite product. It's a natural definition. of the numbers z sub k, and it is denoted by z equal to infinite product n from 1 to infinity zn. All right, so that's a definition. It's a natural definition. We always take the infinite stuff as a limit of finite stuff. The infinite stuff is always the limit of the finite partial sum, partial part. Okay. As we already discussed, it is not necessary. It is natural to require Zn is not equal to 0 for all natural number, for all index and indices n. If one of Zn is 0, then the product will be 0. All right? And then if we call partial product P as a partial product P as a product zkk from 1 to n, then what we have, then first this Pn is never equal to 0. We require all Zn are non-zero. Okay, Pn is never equal to 0. If it's not equal to 0, we can form the quotient. We get Pn over Pn minus 1 is Zn, of course. Okay, and then since we assume this is the sequence Pn converges to Z, then you take the limit. Taking limit, we have what? The limit of Z over Z, the numerator, denominator, is equal to the limit of Zn. Right? So when you take the, I'm saying taking limit of this condition. Okay, and then what do we get? We get the necessary condition. Is the limit of z sub n approaching infinity is equal to 1. It has to be 1. Right? If you have a convergent infinite product, then the general term Zn must converge to 1. The general term must converge to 1. And here, in this part, actually, you know what? We actually take some assumption in our mind. We have P sub n is not equal to 0, but we don't have Z not equal to 0. We know that there's some sequence itself is non-zero, but limit is 0. So this condition holds if Z is not equal to 0. This holds necessary condition is that if Z is not equal to 0. What happens if Z is equal to 0? What happens if Z is equal to 0? So let's check. If Z is equal to 0, then this does not work. If Z is equal to 0, the limit is 0. This condition is not the necessary condition. Okay, this is never the necessary condition. For example, it will be very complex. For example, we have Zn as 1/2 for all n in the natural numbers. if Zn is 1/2, actually you can replace it by any smaller number, positive or negative, it doesn't matter. Okay, if Zn is 1/2, then the infinite product of 1/2 and from 1 to infinity, you actually have 1/2 to the power infinity, right? You have 1/2 times 1/2 times 1/2 times 1/2. It becomes smaller and smaller and smaller and smaller, and eventually it is 0. And the limit of Zn is still 1/2. It's not equal to 1. So the limit of Zn is equal to 1 if the limit of Z is not equal to, the infinite product is not equal to 0. Okay, so that's an important condition, because here you see here you put the Z on the denominator. The denominator is never equal to 0. If Z is equal to 0, if the infinite product is equal to 0, we don't have the necessary condition. If the infinite product is equal to 0, we don't have necessary condition. All right. Okay, so that's a small remark right after the definition. Right after the definition. Another thing, remember that we know that exponential m plus n is equal to the exponential m times exponential n. So the exponential function will map the sum. The exponential of the sum is the product of the exponential, right? So we can do what? We can transform. This is a product, like you have infinite. So we can have something like this. Let's put a t sub k. The product e t sub k. Okay, so if here's k is from 1 to infinity, then this is k is from 1 to infinity. So we can transform the infinite product to the infinite sum, right? Here this t, if this quantity is called z of k, then t is natural log of z sub k. So by the natural log operation, we can transform the infinite product to the infinite sum. Transform infinite product to infinite sum, right? So here's product, and then it becomes a sum. Well, the infinite, the natural log is very good in the real world, but it's slightly tricky in the complex world. So we need that natural log is well defined. So you have to get the principal branch. The principal branch of the logarithm. The principal branch of the logarithm. Okay? So principal branch of logarithm means we're going to cut this complex plane along the negative real axis, including the 0. We are going to cut it. So all the all the zn's should be this place, should be in this area. Well, remember that if the limit is not equal to 0, of course we want to study this case, because this case it contains the necessary condition. And if the infinite product is 0, it's not interesting for our application. We want, because remember we are going to have the analytic function. If you get a 0, it's just zero function. It's not interesting. So we want to study the case when the infinite product is not equal to 0. If the infinite product is not equal to 0, we have the limit of Zn equal to 1. Equal to 1. So eventually, so for sufficiently large n, we can have, or we can assume that Z sub n is all the elements are on the right side, because they are going to be close to 1, so they are going to on the right side of a y-axis. So we assume real part of Z sub n greater than 0, and it does not lose the generality. Okay? So we are going to do this assumption. The real part of the complex number Z sub n is always greater than 0. Possibly for the first few terms, it does not, the real part is not greater than 0. Then you just ignore the first few parts. Start from the case when the Z sub n with the real part greater than 0. The first few terms, you just do the product and it still converges. So the convergence property does not depend on, does not break when you have this condition. All right, so with this condition, and we can study the partial sum of natural log of zk. And with this condition, we can naturally discuss the natural log. We don't worry about the principal branch stuff because it's already guaranteed. Okay, so we get Sn, that's like this part, the partial sum, and Sn converges to S as n approaches infinity. And then we have the exponential of Sn. Exponential of Sn converge to exponential of S because of exponential functions are a continuous function. And this exponential of S is the infinite product of Z n from 1 to infinity. Right? So that's the definition. I mean the process idea. Okay? So remember, again, we have this requirement. This requirement just guarantees that natural log is good. All right. Okay. So let's summarize the discussion we just had. We have the proposition 5.2. So let the real part of Z sub n greater than 0 for all n greater than or equal to 1, then the infinite product Z sub n from 1 to infinity converges to a non-zero, see, non-zero element, non-zero number. We need this non-zero number because this non-zero number, then you have the limit of Zn converge to 1. Okay? To a non-zero number if and only if the series sigma natural log of Zn n from 1 to infinity, this series converges. This series happens to be the exponents of the natural number of the exponential functions, right? Okay. Now let's see. Proof. So if you have the convergent part, like this whole process convergence. If you have this the part converges, then let's see what we need to do. Then first let P sub n be the partial product. P sub n is a partial product, and the limit z is REI theta. The limit of this infinite product is assumed to be REI theta. Here this theta is between negative pi and positive pi. Because we already assume this all the elements Zn have a positive real part, so we define the logarithmic function LP L of a Pn as a real log of value of a Pn and plus I theta n. Here this I theta n should be between theta minus pi and theta plus pi. Okay, so you have that one, you have this theta, and you cut it to the positive and negative pi. Okay, and then we let Sn be the log z sub n plus log z sub 1 plus log z sub n. Okay, then we have exponential of Sn equal to Pn. Well, it's a finite part, finite product, finite sum. They always satisfy this property. Okay, then what is Sn? Sn here you can write it as a sum, but if you write it as a one term, it's Ln L of a P sub n here from here, L of a P sub n and plus 2 pi I k sub n for some integer k sub n. Okay, what is this? How do we get this? Okay, so you see here, when you get this z's L, yeah, when you get those terms, you have the real and the imaginary part. The imaginary part, when you add all these things together, like here, you will actually have the log of z ups value of z1 plus I theta 1 and plus dot 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 and log z sub n and plus I theta n, right? So you just have a lot of individual term, and then you're going to add the log z1 log ups value z1 log ups value zn. They will give you the log ups value. So here the log ups value p sub n is equal to the log ups value of z1 plus log ups value of zn. The real part is okay. The imaginary part has some problem. I theta n is not equal to I theta 1 plus well, let's put a prime here, plus I theta n. It's not equal. You actually have to plus 2 pi I kn for some integer kn, right? You have some rotation there. So that's why when you introduce Sn is not directly equal to L of a P sub n. It possibly has some additional round. Okay, it has some additional round. Okay, so far that's what we have. And now here, P sub n is equal to z. P sub n is equal to z. This is an infinite product. This an infinite product converges. The Sn minus Sn minus 1, which is natural log of z sub n. Natural log of z sub n. And remember that we assume it converges to a non-zero number. If it converges to a non-zero number, all the Zn will converge to 1. Zn will converge to 1. Log Zn will converge to 0. So this will converge to 0. As Zn converge to 1. Right? So then you do the subtraction. Here, you do the subtraction. So you will get L of Pn minus L of Pn minus 1 converge to 0, and this part 2 pi I k n minus 2 pi I k n minus 1 will converge to 0. Right? Here, this one converges to 0 because of this. So Pn converges to Zn, then Lpn will converge to 0. Because you still have the L Pn over Pn minus 1 converge to 1. So you get this converge to 0. And from this converge to 0, this converge to 0. These two conditions imply the second one converge to 0. Okay, not both come from this part. This part comes from the Sn, the difference of Sn and difference of L of Pn, both converge to 0 because of here. Because of this condition. All right, so it's a little bit twisting. Okay, so remember that we have Kn integers. All Kn are integers. If it converges to 0, so Kn is a constant for some 1, n is greater than some fixed natural number. Capital N. So k sub n will be eventually a constant number. Then the difference will be 0. All right? So k sub n will be the natural numbers, some constant natural numbers. So the Sn equal to L of P sub n plus 2 pi I k for n greater than or equal to capital N, and Sn will converge to L of P plus 2 pi I k as n approaches infinity. So what? So Sn converges. So the log Zn, the infinite sum converges. Infinite sum converges. So if you have a convergent infinite product, then the corresponding infinite sum of a log of a Zn will converge. This is one direction from left to right. And conversely, if this natural log series converges, then the infinite product will converge. It comes from here. It comes from the discussion before the proposition. The converse part was proved before the proposition. Why we say before the proposition? You see here, we assume if Sn converge to S, then exponential Sn converge to exponential S, and then exponential of Sn will be the infinite product. You see here, we start from assumption of a convergence of a series, and then we get the convergence of the product. And this part, we start from the convergence of product, we get the convergence of series. See it? So we finished the proposition 5.2. Okay? So the product series, they have some equivalent relation. And be careful, there are two conditions. One, the real part of Zn is always greater than 0. Two, the infinite product is not equal to 0. And this condition is used here. Yeah, is used here. The natural log will converge to 0. Otherwise, we don't have this part. Otherwise, we don't have the natural log of Pn minus natural log of Pn minus 1 converge to 0. That one we don't have. Okay? Okay, now let's study a little bit of convergence of a natural log. Natural log. Natural log function has a Taylor expansion. Okay, so it's a z minus z squared over 2 plus z cubed over 3 minus z to 4 over 4 plus z to 5 over 5. Remember that it's alternating alternating series. And denominators are always the exponent of the numerator. Okay, so this is a Taylor expansion around the 0. And the radius convergence is 1. Okay, so if we simplify it a little bit, we will see the following thing. If we still use this condition, then we will have 1 minus natural log of 1 plus z over z. Okay, so we first factor out z. We factor out z to the division, and you have a 1. And then you're going to move the tail to the left side, this term to the right side, you have this. You put the up's value, it is equal to up's value, then you have a z over 2 minus z squared over 3 plus z to 3 over 4. Remember, you do division once, so the exponent decreases by 1. Okay? But this is still convergent series inside it. All right, and then you apply the you apply the triangle inequality. It's less than or equal to each term. So 1/2 z plus 1/3 z squared plus 1 over n z to n minus 1. And you replace all the rational numbers by 1/2. And this is a geometric series. It is equal to 1/2 the initial term over 1 minus a ratio. Remember that we assume this ratio is less than 1. Okay, so that's it. For this one, we have even further assumption. If we further assume that up's value of z is less than 1/2. Up's value of z is less than 1/2. It just means we can control this. We can control this. We can control this what? We can control this up's value of z over 1 minus up's value of z less than 1. You check that when under this condition it's less than 1. Because it's less than 1/2, the numerator is bigger than the denominator. Okay, less than 1/2, 1 minus this number is going to be greater than the numerator. So it's less than 1. Less than 1 times 1/2. This right side is less than 1/2. When it's less than 1/2, you apply the up's value stuff here. You will get you will get the natural log of 1 plus z. Ops value is bounded by 1/2 z and 3/2 of z. Ops value. Okay. Okay, so this is what we need. And with this condition, with this information, remember that this information holds, or this inequality holds if ops value of z is less than 1/2. We have the following proposition. Proposition 5.4 is that let real part of z sub n is greater than -1. Real part of z sub n is greater than -1. Why we need this? Because when this is greater than -1, this one makes sense. Okay, then the series natural log of 1 plus z sub n converges absolutely if and only if the series sigma z sub n converges absolutely. Right? And this condition is, this proposition is a direct application of this one. Okay, so the proof. If series z sub n converges absolutely, if this one converges absolutely, you're going to consider this one, the absolute natural log of 1 plus z less than or equal to 3/2 of ops value of z, and it's dominated by a convergent series. So the series converges absolutely. Okay, and if the other way, if this converges absolutely, then you will consider the series. You will consider the relation. You will consider this relation. So the series of z sub n converges absolutely. Right? That's whenever you have some relation like this, you can say that the convergence property of those two series will be equivalent. All right, so that's the proof. Oh well, let me make this extremely clear between those two parts. We still have a few minutes. Let me make this clear. Okay, so back to this condition. How do we get this 1/2, 3/2 stuff? If ops value of z is less than 1/2, then you can prove this one is less than 1. Just use this. And you do the product, you will get this. Okay, so you have this difference ops value. Ops value of the difference less than or equal to 1/2, and we're talking about the zeros. Z is not equal to 0, so we multiply this by z. You will get multiply this inequality by ops value of z, you have this, right? And then what is else? By the triangle inequality, remember this natural log of okay, so you write this minus z plus z, then apply the triangle inequality, you have this. This is this will give you the 3/2, and this part you also have the triangle inequality. A minus b is greater than or equal to ops value of a minus ops value of b. So here you use z minus ops value of z minus natural log of 1 plus z. And this is a z minus 1/2 ops value of z. It's a subtraction, so it's greater than. Okay, so here's a less. Where is it? Yes, this is less than 1/2. Less than, and when you put the negative sign to be greater than, so that's why here is a greater than. This direction, yeah, it's greater than this. Then you will get 1/2 ops value of z. Okay, so it's just a algebra. Try to do it if I don't make myself clear. Okay. All right. Okay, so that's enough. I will continue this discussion in the next video, and we'll talk about absolute convergence. And be careful here. This proposition is about convergence absolutely. The previous proposition is just a convergence. Okay, there's some difference. And also, we already have the absolute convergence for the series. Series, we have absolute convergence. But so far for the product, infinite product, we only have convergence. We don't have absolute convergence so far. So next, we're going to discuss absolute convergence for the infinite product. Okay, thank you.